let's talk about how to calculate the lengths of secants, chords, and tangents. If two chords intersect in a circle, then they form chord segments. AF, EF, DF, and BF are all chord segments in circle C. And the product of the chord segments of one chord is equal to the product of the chord segments of the other chord. But why? Well, let's write a proof. Given that AE and BD are chords of circle C, which intersect at point F, prove that AF times FE is equal to BF times FD. First, we're going to need to draw two segments. We need to draw segment AB and segment DE, which we can do because between any 2 points, a line can be drawn between them. So our goal is actually to prove that the two triangles that we just created by drawing those segments are similar to each other. To get started, we can use vertical angles. AFB and DFE must be vertical angles by the definition of vertical angles, which means they must be congruent to each other by the vertical angles congruence theorem. Also notice that angle ABD and angle DEA are both inscribed angles because they're angles whose vertex is on the circle, and these two angles have a common intercepted arc. That would mean that those two angles are congruent to each other because inscribed angles with common arcs are always congruent to each other. So now I have shown that those two triangles are similar to each other using angle-angle similarity. And since they're similar, their pairs of corresponding segments must be proportional. So I can say that AF over FD is equal to BF over FE by the definition of similar polygons. So I could cross-multiply and show my proof statement that AF times FE, the product of one chord's chord segments, is equal to BF times FD, so the product of the other chord's chord segments. Next, let's talk about tangent segments. If two tangents intersect outside of a circle, then they form tangent segments. So GH is a tangent segment and IH is a tangent segment. And the lengths of these two tangent segments are equal to each other. GH is equal to IH. But why? Let's write a proof. Given that GH is tangent to circle C at point G, and IH is tangent to circle C at point I, prove that GH is equal to IH. We're going to start in somewhat of a similar fashion to the previous proof that we need to draw some segments first. I'm going to draw segments GC, IC, and CH. Doing so creates two triangles, and our goal is to prove that those two triangles are congruent to each other. The first thing I would know is true is that angles CGH and CIH are right angles by the definition of a tangent to a circle. If GH is tangent to circle C at point G, then it has to be perpendicular to radius CG, which means it forms a right angle. And same thing with tangent IH and radius CI. I can also see that those two triangles share a side. CH must be congruent to CH by the reflexive property of congruence. And since CG and IC are both radii of circle C, they must be congruent to each other by the definition of radius. So I can now show that those two triangles are congruent to each other by HL. They're both right triangles, their hypotenuses, CH, is congruent to each other, and they have a pair of legs that are congruent to each other, so the triangles must be congruent to each other. And if the two triangles are congruent, then all of their pairs of corresponding parts are congruent, and the pair of corresponding parts that we're interested in for this proof are the tangent segments, GH and IH. Those are corresponding parts of those two congruent triangles, so by CPCTC, they must be congruent to each other. Now let's talk about secant segments. Secant segments are a little bit different because when they intersect outside of the circle, they actually create an extra segment called an external segment. So JN and LN are secant segments. They're the entire thing from one point on the circle through another point on the circle to the point of intersection outside of the circle. This whole segment is a secant segment. But the part that's on the outside of the circle, KN or MN, those are called external segments. And what we know about secant segments and external segments is that the product of a secant segment and its external segment is equal to the product of the other secant segment and its external segment. But why? You guessed it, we're going to write a proof. So given that Jn and Ln are secant segments and Kn and Mn are external segments, let's prove that Jn times Kn equals Ln times Mn. We're going to start the same way as the other two and draw two segments in order to create two triangles. And our goal is to show that these two triangles, JMN and LKN, are similar to each other. Well, the first thing I notice is that those two triangles share angle N, and angle N has to be congruent to itself by the reflexive property. I also notice two inscribed angles with a common arc. Angle KJM and angle MLK must be congruent to each other because inscribed angles that intercept the same arc are always congruent to each other. So now I can show that those two triangles are similar using angle-angle similarity. And if they're similar to each other, then each of their pairs of corresponding sides must be proportional. So I can say Jn, which is the secant segment, over Ln, which is the other secant segment, is equal to Mn, which is an external segment, over Kn, which is the other external segment. And then cross multiply, and we have proven that Jn times Kn is equal to Ln times Mn. And finally, let's talk about the intersection of a secant and a tangent. A tangent segment is something like Gn, we already talked about that, and a secant segment is something like Ln, and Mn would be its external segment. So this is kind of a combination of the last two proofs put together. And what we end up showing is that if you square the length of the tangent segment, it's equal to the product of the secant segment and the external segment. And it's actually going to take us 10 steps to prove why. So given that Gn is a tangent, Ln is a secant segment, and Mn is an external segment, let's prove that Gn squared is equal to Ln times Mn. We're going to draw segments GM and GL, and our goal is to prove that triangle GMN is similar to triangle LGN. So this little triangle out here, we're going to prove that it's similar to the entire triangle. I notice once again that they share angle N, so I can say that N is congruent to N by the reflexive property. I see that angle GLM is an inscribed angle, and I know that an inscribed angle is equal to half the measure of the intercepted arc. So the measure of angle GLM is equal to 1/2 times the measure of arc GM. And likewise, I can say that the measure of angle MGN is equal to 1/2 of that intercepted arc as well. So since both of these angles equal 1/2 the measure of arc GM, I can say that they equal each other by either the transitive property or the substitution property, depending on how your brain thinks about it. They're both equally correct. And since they're equal to each other, they must be congruent to each other as well by the definition of congruent angles. So I now have enough information to say that this triangle right here on the outside, triangle GMN, is similar to triangle LGN because of angle-angle similarity. And if they're similar to each other, then each of their pairs of corresponding sides must be proportional. So I can say something like GN, that's the side that connects the 2 marking angle to the 1 marking angle, over LN, that's 2 markings to 1 marking, that's that side, is equal to MN, that's the side that connects the no marking angle to the 1 marking angle, over GN, which if you're looking at the entire triangle, the no marking side is this angle, and the 1 marking is N, so GN. So then you can cross multiply, and we have shown that GN squared is equal to Ln times Mn. So that was a lot of information that we just covered, and the easiest way to sum it all up is that chords, if they intersect inside of a circle, you multiply the chord segments together, and they're equal to each other. If tangents intersect outside of a circle, then the tangent segments are just equal to each other. If secants intersect outside of a circle, then you multiply the length of the entire secant segment by the length of the external segment. And if a tangent and a secant intersect outside of a circle, then you square the length of the tangent and set that equal to the length of the secant segment and the length of the external segment multiplied together. So let's try a few examples. The first thing you need to do with all of these types of examples is identify what kind of segments you're looking at. And since these are segments that intersect inside of the circle, Each of these segments connect 2 points on the circle, but they don't extend outside of it. These must be chords. And what we know about chords is that you can multiply the 2 chord segments together for one chord, and that'll be equal to multiplying the chord segments of the other chord. So we're told that QU is 6, UT is 3, and RU is 9. And I can call US X. So the equation that I'll write is that 6 times 3 is equal to 9 times X. So that's the chord segments of chord QT multiplied together, and I set that equal to the chord segments of chord SR multiplied together. So that's 18 equals 9X, so X must be equal to 2. Let's try another one. First thing you need to do is identify what kind of segments you have. And these are tangent segments. They intersect the circle at only one point, and I know that tangent segments are equal to each other. So since QR is 3x plus 5 and QS is 5x minus 9, I can just set those equal and solve. So X must be 7, and I can plug 7 in to figure out the lengths of each of those chord segments, and as you would expect, they're the same length. If you had gotten different lengths, you would know you had done something wrong. In our next example, we have 2 secants that are intersecting outside of the circle. These are secants because they intersect the circle twice and they extend outside of the circle. That makes it a secant. So QS is a secant segment and RS is its external segment. Likewise, US is a secant segment and TS is the external segment. And what we know about secant segments and external segments is that if you multiply the secant by its external, it's equal to multiplying the secant segment by the other external segment. So since QR is 11, and RS is 9, and TS is 10, I'll go ahead and call UTX. So the equation that I'll write is this. The length of the secant segment is 11 plus 9, so it's that whole thing from Q to S, so that would be 20. And I'll multiply that by its external segment, which is 9. So far I have 20 times 9 equals, and then I need the length of the entire secant segment, which would be x plus 10, and I'll multiply that by the external segment, which is 10. So I have 10 times x plus 10. And if you distribute, you get 10x plus 100. Subtract 100, divide by 10, and we find out that x is 8, which means UT is 8. On the next example, we have a secant segment intersecting a tangent segment. QS is a secant because it intersects the circle twice and it extends outside of the circle. TS is a tangent segment because it only intersects the circle once. And what we know about tangent segments and secant segments is that if you square the tangent segment, it's equal to the product of the secant segment and its external segment. So since we're given that QR is 10 and RS is 8, we can call TS x and solve. So I'll say that x squared, the tangent segment squared, is equal to the length of the secant segment, which would be 18, times the length of the external segment, which is 8. So 18 times 8 is 144, square root, and we find out that TS, the tangent segment, must be 12. And that's all you need to know about calculating the lengths of tangent segments, secant segments, and chord segments. In our next lesson, we'll learn how to graph a circle in the coordinate plane.